Hi everyone, my name is Sjoerd and I'm gonna give a talk about scalable selective sweep classification and detection. I will start with some background about the motivation of this research, namely some problems that exist in terms of scalability, and especially when using our classification model to perform detection of selective sweeps, for instance, when doing whole genome scans. And I will give some background on the signatures of a selective sweep. And I will continue on some of the background that Hansin already introduced. So firstly, on the scalability of using convolutional neural networks for selective sweep classification. As you know, modern data sets can contain thousands of genomic samples due to modern alignment methods. And these can then again consist of millions of SNPs, making the entire data size very large, and CNNs can take a significant amount of time to process all of this data, as the complexity of CNN scales linearly with the width and the height of our input. So some methods that are being used to implement CNN classification for selective sweeps, as Hansin said, is using raw SNP data. But an issue with using raw SNP data is that the processing power required to process all of this data increases as we increase the number of samples that we add to our data set. So the scaling with this kind of data becomes problematic. A second method that's often done to further improve the classification performance, as we have also just seen, is reordering. Reordering can slightly improve the classification accuracy. And thirdly, using, again, summary statistics, we can also improve classification. However, this makes the method more problem specific and less flexible than just using raw data. And furthermore, this requires compute intensive pre-processing. And both of these methods are a form of window-based pre-processing. So based on the window that we take to have a window of SNPs, we do pre-processing. And that becomes a problem when we want to transfer a model from just classification to detection. So why is that the case? When we do detection of selective sweeps on a whole genome, for instance, we can sample windows throughout the genome and classify each window individually to find out where on this genome this selective sweep might occur. But if we want very precise detection of selective sweeps, then we want to sample a lot of windows from a lot of different positions along the genome. And moreover, using wider windows can lead to better classification. But when we sample windows in a fine-grained way, and especially if the window size is rather wide, this can lead to significant overlap between different windows. And if we want to separately classify each of these windows in a most simple way, we would have to do a lot of repeated computations because each overlapping section would be computed separately, again, for each window that contains this section. But fortunately, CNNs can do this more efficiently by the nature of their architecture. So why is that? CNNs are translationally equivariant, which means that the input of a CNN in one position leads to an identical output if it's in another position, as you see in this example over here. Shifting the position of the input does not change the output, only the position of the output. Using this characteristic, we can actually reuse a lot of computations in the intermediate steps of the convolutional neural network within overlapping windows. As you see in this example, when we have multiple windows, they use the same features to eventually get to their final outputs. So recomputing each of these features for different windows is unnecessary. Moreover, if we benefit from reusing all of our data, the complexity in terms of with respect to the window width that we use as input is nearly constant with the width of the input. However, one problem that arises with this if we use a lot of layers which have a stride of greater than 1. And we often do this, especially when we use pooling layers. We often use pooling stride of 2, or for instance. And what this influences is that we do not get as many outputs as we might want for fine-grained detection. However, we can overcome this problem by transforming our network. And we can do this by removing the strides from these layers that use a stride of greater than 1, and using dilated convolutions in the subsequent layers instead. And if this is done for all layers, we can actually get one output for each input column, so SNP column, for instance, that we give. As you see here, the output is more dense except for some edge values. And in this way, we can actually fully reuse all the available computations for overlapping windows, making detection much more efficient. But again, all of these advantages are not cannot be applied if we use window-based pre-processing. So that's why we try to find a method for selective sweep classification that does not do any of these pre-processing steps and can therefore be implemented as an efficient detection method for selective sweep detection. So going back one step again to the signatures of the selective sweep, we look at 3 main signatures, which, as briefly explained already, is the pattern in the linkage disequilibrium, the shift in the side frequency spectrum, and the local reduction of polymorphism. We're going to focus mainly on the latter 2 because we find that using the linkage disequilibrium will make our approach computation intensive, and we want to see if we can avoid having to use this and still get good results even in the presence of confounding factors. So the shift in side frequency spectrum and the reduction in local polymorphism can be visually quite seen when you look at these SNP matrices, one for selective sweep and one for neutral data, where the distances vary quite vastly, and also the side frequency spectrum can be already observed from the image. So how do we make these features scalable, and how do we make good effective architecture to use these features for classification? So what we want is a network which uses only 1D convolutions and has only one-dimensional input, so the complexity is irrespective of the sample size. And we want to encode the side frequency spectrum and the density of polymorphism in a one-dimensional way. And we do not want to use any pre-processing steps because that will hinder efficient transferring to selective sweep detection framework. So firstly, to start out with the density of polymorphisms, we can do this by including the positions of the SNPs in our data. However, the way we have to do it, we have to think about it a little bit, because if we just use the positions of the SNPs themselves, then this can easily lead to bias when training a model. For instance, if we always simulate data with the sweep in a certain position, then the model can actually just learn where this position is, and we will not actually learn valuable information. We can also use the relative SNP positions maybe. So the position of a SNP relative to, for instance, the first SNP position in the image. However, this is actually a form of image-based pre-processing, because if we shift our window by a certain amount, then the position, the relative position of each of our SNPs will actually change. So this also won't work when we want to transfer this method to efficient detection. So instead, we can best use the SNP distances between neighboring SNPs, which can be done using a factor such as this, which is translationally equivariant, so will be easy to transfer to efficient detection. Then for the side frequency spectrum, we can simply compute the frequency of the derived alleles in our matrix, which also makes this vector independent of the sample size and is very inexpensive to compute. And we have to store a lot less data and transfer a lot less data to our computing hardware. To fuse these two features, we explore two different methods. So either we can use early fusion. Early fusion means that we combine these two features at the start of the network, and we use both features as different channels as input to our CNNs. And that way the model is able to combine the features to maybe find more information using the combined features about the selective sweeps. And the other way is late fusion, where we actually process the SNP matrix separately first, and then at the end of the network we add the SNP distances as additional inputs to the fully connected layer. And to optimize the model itself and to make sure that we don't miss accuracy because of a certain architectural choice, we do a small model architecture search, starting out with the base of a SweepNet architecture. And the search space includes the number of layers that we use, the number of channels that we use per layer, the kernel size, and the kernel stride. So let's see the results and what this leads up to. So first, just looking at the fusion of the two features that we discussed. By using, in each sample, each data set, which includes the 6 data sets that were also covered in the previous presentation, the first two being population bottleneck data sets, the second two containing migration, and the third containing selective sweeps within recombination hotspots. We see that in each case, including the SNP distances, improves the classification accuracy, but using early fusion, the accuracy increases significantly more. The model architecture search gives the following results, where a model with 3 convolutional layers, 80 channels, and a kernel width of 2 with a stride of 1 gives the best accuracy performance. Moreover, we noticed that if we would add more layers to our model, the model would actually overfit, being the reason that these models do not perform as well. So then using derived allele frequencies instead of the entire SNP matrix, if we compare the model using the early frequency, using the early fusion of the SNP positions with a model that uses the derived allele frequency and early fusion of the SNP distances, we see that using only derived allele frequencies on almost all datasets, the accuracy stays the same. We only have a slight drop in accuracy on one dataset over here, which is from 96 to 94% accuracy. So not a huge drop, whilst the execution time of these two models differs quite significantly, especially when looking at the performance on the CPU. Training and inference can go significantly faster depending on the width of the window. And since wide input windows can lead to more accurate classification, this can be quite an important difference. On the GPU, the effect is less significant. This is because at this point, the bottleneck in performance is mainly transferring data to the GPU, which could be resolved maybe by a more effective implementation of communicating the data to the GPU. Comparing the performance to other methods, which includes raw SNP-based methods and summary statistics-based CNN methods, we find a greater or equal testing accuracy on these data sets that we discussed. And consistent with the previous observation, the execution time is reduced significantly, making the model just much more efficient than other methods. Then going back to the transferability to efficient detection using this classification model, we perform a whole genome scan with a model trained on simulated data of purifying selection on the human genome. We scan the 22 autosomes, and this contains over 12 million SNPs. And we can actually perform this whole genome scan with a dense output, meaning that we get one output for each input position in less than 2 minutes on the CPU. Yeah, so that's pretty fast. So the lessons learned from this, using a allele frequency-based method is almost as efficient or as effective as using a raw SNP-based method, and it scales much better with the sample size. When fusing SNP distances, it's much more effective to use early fusion than to use late fusion. And we find that we do not need to use any pre-processing to attain this, making the method transferable to efficient detection. We have implemented this method in an open source tool that is nearly released, which is an extension of an existing tool called RAIST. RAIST uses summary statistics to compute or to detect selective sweeps, and RAIST AI is extended by using the methods that are here presented, and it makes it very easy to train your own models in any kind of data and to perform selective sweep detection in a short amount of time. And it uses an optimized C backend and PyTorch for training and inference of models. So to quickly show you how easy it is to use RAIST AI to do these experiments yourself, using RAIST AI, you can take MS files that you have generated and easily, through the command line, generate training and testing images by simply specifying the length of the simulations in base pairs, the location of the sweep, and specifying that this is image generation. You can do that for training and testing data sets, and then you can very easily train the model presented, or maybe a model that you design yourself, by specifying the generated image data and the number of epochs that you want to train for. And using the trained model, you can test the performance on classification to check that the model trained properly. And finally, you can also use this model then to implement detection, and RAIST AI will give you an output such as this, where you can, in this case, see easily where a selective sweep is located in a given data. You can specify the number of grid points that you want to use for more fine-grained or more coarse detection. That's it. Thank you for listening.